Hey everyone, welcome to a new series where I will talk about the physical limitations of game engines. We will talk about how and why these limitations exist, and more importantly, how to avoid them or go around them if necessary. If you're creating a video game, physics-based or otherwise, or simply interested in physics and simulations, this one's definitely for you. So let's dive right into it. Before we begin, I'd like to say that this video has examples from Unity game engine, but applies to most if not all game engines in general. Also, while game engines do an overall good job simulating physics, some of these limitations can impact even relatively simple games, so you probably have encountered something similar while developing your own games. If you didn't, don't worry, it's coming. Creating a fairly accurate physical simulator is very difficult. Creating a totally accurate physical simulator is impossible. While there are many reasons for this, the main one is due to the most basic limitation of computers, that they are discrete. And no, I don't mean that in the sense that they're keeping your secrets, because they don't. Which reminds me, this video is sponsored by FjordVPN, No, it doesn't. Just continue with the video, please. Dude, I'm trying to make us a living here. Dipshit. When explaining the concept of discretization, it is usually easier to look at signals as an equivalent, more familiar example. So in our case, the signals are everything that's happening within our game. Every object movement, every health bar draining, everything is a signal of its own. If something changes rapidly, it's a rapid signal. For example, an object with high velocity is changing its location rapidly, and vice versa. Generally, signals are divided into continuous and discrete. While continuous signals are smooth and infinitely dense with information, discrete signals are less smooth and contain information only in specific points. For example, take this beautiful sine signal. It looks continuous and is very smooth. In a continuous signal, I can choose any point along this line and calculate its value. However, as you can probably tell, this is not really a continuous signal. If I zoom in enough, you can see that it is actually made of discrete points with nothing in between. Here, each point represents what's known as a time step. In GameMaker jargon, we call it physics update step. So in our game engine, just like this plot, the game world does not exist in between the steps, but rather it is compiled from a series of discrete moments. Therefore, if an object is supposed to collide with another object in the space between two adjacent steps, it will clip through. Game engines do have a fix for that, but it also has its limitations. When we play a game, we are usually playing in this setting. We have a relatively low physics update rate and a relatively slow game. Therefore, everything looks smooth, and for the most part, it's fine. Increasing the physics update rate does not improve the game experience in a meaningful manner, and so it is not advised. So we can say that this level of discretization is good enough for most uses. But there are many cases when this is not, usually when a very fast and accurate motion is required. In these cases, our game looks more like these two graphs, where a high physics update rate manages to handle fast movements, but a low physics update rate doesn't, and we end up with a mess instead of a coherent experience. We can summarize this notion in this graph. We can have a low physics update rate and slow movement, which is usually fine. Or we can increase our physics update rate so it can handle both slow and fast movements up to a certain point, but at the price of station demand. The troubles begin when we get to the lower right end of the plot, where the physics update rate is not high enough to compensate for the maximal object rate of change. So, we can divide the graph in this fashion. We want to be in this part and avoid this part. By the way, if we are really looking for optimization, we want to be on this green line, where we make the most out of our calculations. Any higher and we'll be wasting computer power. Any lower and we're dangerously close to discretization errors. Okay, let's move away from graphs for a bit and get back into gaming. Here are some familiar game scenarios that feature a discretization error. As you can see in these examples, the colliders are updating their location every step, and if the steps aren't close enough, it can lead to clipping. So what can we do to get around this limitation? Remember this graph? We would want to move from the right side to the left. How we go about this depends mainly on our game, and it can be either improving the physics update rate, tweaking the game, or a mix of these two. Here's what I mean by that. If these examples are something that occurs in your game but not very often, then fixing the game might be the simpler option. In this context, setting a maximum velocity can solve the issue. Then the objects will not move fast enough to clip through each other in between steps. Using this fix means compromising on the end product, so we need to be sure that the velocity limitation doesn't make the game any less fun. We must not forget that games are more about being fun than about being physically accurate. But what if your game relies on being physically accurate? Or there's a section in your game that has very rapid changes that you just can't leave out? Then we can try either one of the other options. Increasing the physics update rate is a common solution. For this reason, game engines include an option to increase the overall physics update rate of the game. As I said, however, it comes at the price of performance demand, and so the system requirements of the game may go up. To increase the physics update rate in Unity, simply head over to the editor, click on Edit, and navigate to the project settings. In there, inside the time ribbon, you will find the fixed time step setting. The fixed time step is 1 over the physics update rate. So if you want to increase the physics update rate, you need to decrease the fixed time step. The default physics update rate is 50 Hz, or 50 times per second, so the fixed time step is 0.02 seconds. Another, arguably better solution along this line is if your game isn't always very rapid, but has some rapid sections, you can set the physics update rate from the code in the Game Manager script. To do this, all we have to do is write one line of code to change the fixed time step. We write time.fixedDeltaTime equals 1 over our desired physics update rate. Another less common option is to enable substepping. This will make the engine calculate the physics multiple times per time step. This is very similar to simply increasing the physics update rate, which is why it is less common. Here are some tips for when dealing with discretization errors. Try enabling continuous collision detection for fast objects. This can help avoiding changing other things such as object velocity or the physics update rate. Please note that this will only work on physics-related detections, and so triggers, for example, will not be affected. So, if I want to fix the issue with the coins or fast projectiles, I will have to change their detection from trigger-based to collision-based in the code. Another tip I have for you is that you should be very cautious when changing the fixed time step, because it can affect your game in many ways that are hard to anticipate. For example, any method that applies an effect over time might need a total new set of parameters to work properly again. So be mindful of that. Alright, that's it for this video. I hope you enjoyed it and learned a lot from it. If you did, please consider leaving a like and subscribing, as I plan to create a lot more of this content in the future. Thank you for watching, and I'll see you in the next one. Cheers, guys!